Hey, okay, good night. Yep. Good night, everyone. Okay, before we get started, I just wanted to say a few things about this assignment 4. So, the first thing is just like it doesn't actually affect um the question or anything, but I do have like a typo, so the definition in question 2, it should say it's for positive semi-definite, not positive definite. Like it doesn't actually affect what the answer is or anything. But if you go out in the world, positive semi-definite means that all the eigenvalues are greater than or equal to 0, while positive definite means all the eigenvalues are strictly greater than 0. So I didn't want you getting the wrong idea. Again, if you, oh, yeah, just saying that positive semi-definite, so a n by n matrix such that A transpose equals A, and all the eigenvalues of A are greater than or equal to 0, that's called a positive semi-definite matrix. And the same thing, except all the eigenvalues are greater than 0, strictly greater than 0, that's called positive definite. So just for your information, if you have already done this question, then what I said doesn't change what you wrote down. So it's more like for your, for the future, if you ever meet these in the wild. Okay. I also wanted to make some mention of, the first question. So we have this matrix whose transpose is negative of the matrix. A matrix like this is called skew symmetric. And just to give you an idea, let's see, just to give you some ideas about this question, to check that it's normal, you have to check, okay, so for a real matrix, a matrix with real entries, A star is just the transpose of A. So to check that K is normal, you just need to check that K transpose K equals K transpose. And then that means you have to check that negative K times K equals K times negative K. Okay, so that's how you check that K is normal. Once you know that K is normal, you know that you can write K as UD U star, where U is some unitary matrix, D is a diagonal matrix. And then remembering how like that what the star does, well, to compute K star, well, another way of doing K star is just UDU star, and now UDU star is just, you take the star of everything but reverse the order. Okay, so U star was like on the rightmost, well, it becomes the leftmost and it gets a star. D gets a star and comes next, and then U gets a star and it's last, so U star. And of course, U star star is just U. D star is D star, and we have U star. Okay, but another way of writing, so since K has real entries, K star is just K transpose, which is negative K, which is negative UD U star. Okay, so that's for part B. Just compare this equation for K star and this one and see what that says about this diagonal matrix D. Okay, and then for the last part, it's just to know that if you take, if V is an eigenvector and lambda is an eigenvector, or let's say instead of lambda, it's something I want to type, say C is an eigenvalue, we have KV equals CV. Well, since K has real real entries, you can take the conjugate of both sides of this equation, and what you get is K V equals C V. So everything, you just conjugate everything. I'll put bars. Okay. But K has real entries. So if you conjugate all the entries of K, you just get K back. So that tells you that K V equals C bar V. Okay, so what it tells you is that you know, oh, and I forgot a bar over V bar over V. Okay. Okay, so what it tells you is that if C is an eigenvalue, so is C conjugate. Okay, but the part B also says that D star equals negative D. Okay, so that tells you that C bar equals negative C. Okay, now if you try and find complex numbers whose conjugate is just the negative of the number, if you think about, well, if you work it out, you'll see that there's only two possibilities. Well, yeah, they're all of the form I times the real number X. If you combine this all together, that kind of tells you what's going on. Okay, so I think that's as much as I want to say for now. Okay, so I'm just writing that that's something we have to check. Yes, it is, like both sides are just negative K squared. But yeah. Yeah, yeah, okay. In fact, you can, like, if you ever want, you know, another, like, if you know, let me, you know, you can do some, like, there's other examples like that, you know, like, suppose A star is, maybe A star is like A squared plus A plus I or something. Then you can show, then A is normal. Why? Well, you just check A star A, That's just a squared plus a plus I times a. And then a star. They're both the same. Okay. And in fact, if you can write a star equals some polynomial of a, right, then a will be normal. Okay, and then the case of skew symmetric matrices is just a special case of that, where a star, where the polynomial p is just like p of a is just negative a. You know. Okay. So I hope that it kind of gives you something to go on for assignment 4. As far as marking goes, I'm still marking assignment 3, but I should be done soon. Yeah. Okay. So, and as far as like topics left in the course go, this week we're going to talk about Jordan normal form, and then next week we're going to cover the singular value decomposition, and that is pretty much going to be it. Yeah. Let me just check so when will assignment 5 be due? Just a sec. Yeah, it'll be due on the 26th, and then the exam 2 will be the 27th to whenever the Sunday is. 27th to yeah, I think the exam has to be from the 27th to the 29th. 26th to 29th. That does, I think I did say that. Okay. So I think the assignment 5 should really be due Wednesday in that case. And then coursework 2 will start the day after to Sunday. But thank you for checking up on that, for bringing that up. Okay. Okay, so let's get back to this thing called the Jordan normal form. Okay. Just to remind you, or if you don't remember, that's okay, but we have the idea of a T, if T is a linear transformation from V to V, then we have the idea of a T invariant subspace. And U is called T invariant if T of U is a subset of U. Okay. And what we want to do is we kind of want to find, like, we want to decompose the vector space V into as many T invariant subspaces as we can. And the idea is, so let me kind of write down the idea. The idea is, if V is U plus W, a direct sum, and U and W are T invariant subspaces, then when I compute the matrix of T, as long as I use as long as the bases that I use come from U and W, this is the matrix that I get. I get a matrix A here, and I get a matrix B here, and I get zeros here and zeros here. Okay. So what happens where A is the matrix of T, but restricted to go from U to U, and B is the matrix of T restricted to go from W to W. Okay. And so, like, for example, maybe V has dimension 4. So that means, like, the matrix of T would be a 4x4 matrix that has 16 entries. But if we can decompose the matrix into, like, these two matrices, well, A and B will both, like, so let's think about, just briefly, let's think about an example. Say that the dimension of U equals the dimension of W equals 2. Then A and B are 2x2. And, you know, so that means, like, the only relevant values for the matrix of T will have 4 non-zero things in A and 4 non-zero things in B. So because because U and W don't interfere with each other, that makes T a lot easier to understand, just because 2x2 matrices are easier to understand than 4x4 matrices. As another example is that if U is an eigenspace, we'll say that U is the null space of A minus 2i, and W is the null space of, say, like A plus I, and if V is U plus W, direct sum, then what happens to the matrix of T? The matrix of T on U, sorry, not the matrix of T, like, was the null space of A minus 2i. On U, A just looks like, oh yeah, this should be T's instead of A's. Sorry. T's. Okay. So on the vector space U, T minus 2i is always 0. That means T is equal to scalar multiplication by 2. So on U, you just get a bunch of 2's on the diagonal. And then on W, t plus I is 0. So t is just multiplication by -1. So then you have some like -1s. Or something like that. Okay, and then zeros everywhere else. Okay, and then in this case, you know, t is it's pretty easy to see what's going on, you know, like t takes some of the vectors and multiplies them by 2 and takes some other vectors and multiplies them by -1. Okay. Okay. So that's our goal, is to find the nicest decomposition we can. Of course, if we have if the matrix of T is like normal, then we have an exceedingly nice decomposition. We just have like diagonalization. But you know, not all matrices are diagonalizable, and so we want something to do in case diagonalization doesn't work out. Let's just do a quick example of a matrix that is not diagonalizable. Okay. What about the matrix A? This is going to be the matrix 0, 1, 0, 0, 0, 1, 0, 0, 0. Okay. You know, the first thing you can check is that A is not normal. You know, what's A transpose times A? So to compute that, I take, so let's see, I take the first column of A and multiply it by A. So I get 0, 0, 0. And then I think I also still get zeros here. And then I get, well, it's better, better just to multiply it out. Sorry, I'll just multiply it out. So A transpose is like this. And then A is like, so when I multiply these two matrices together, what do I get? I get zeros in the first, zeros in the first row. And then I get this row times this matrix gives me 0, 0, 0. And the last row times this matrix gives me oh wait, I did that wrong. Here, this should be not 0, 0, 0, but it should be 0, 1, 0. And then the last entry should be 0, 0, 1. Okay, so yeah, and then what's AA transpose? Well, we just what's that? Well, I just patiently multiply it out. What happens? Okay, well, I get 1, 0, 0. Already I see I get something different. And then I get 0, 1, 0, and then I get 0, 0, 0. So I get two different things when I do A transpose and A transpose A. So here we have a matrix that's not normal, so it's not unitarily diagonalizable. And in fact, it's not even diagonalizable at all because what's the characteristic polynomial of A? PA of Z is just the determinant. Just the determinant Z minus 1, 0, 0, Z minus 1, 0, 0, Z. So that determinant is just Z cubed because this is an upper triangular matrix with Z's on the diagonal. Okay, if you factorize this is Z times 0 cubed, telling you that the only eigenvalue of A is 0. Okay, so any basis of eigenvectors, they all have to come from the eigenvalue 0. If you compute the null space of A minus 0 times I, well, that's the null space of A. What's the null space of A is just the set of all the vectors whose first entry can be anything and the other entries are 0. So you have like the null space of A is things like A, 0, 0, like that. Okay. And a basis for the null space is just the first standard basis vector E1, 1, 0, 0. Okay. But this is the only eigenvalue. So if A is diagonalizable, this one eigenvalue has to provide all the eigenvectors. This should be P subscript A. And I just write an underscore for a subscript. Right, so meaning the characteristic polynomial. Let me be more. This is determinant, and let me draw an arrow. P sub A is just determinant of Z times the identity minus A. Okay, the characteristic polynomial tells us all the eigenvalues. This one tells us that there's only one, but this one eigenvalue only provides us one eigenvector. Okay, where we needed 3. We needed to find if A was diagonalizable, we'd have a basis of R3 consisting of eigenvectors. There's only one. Okay, so A is not diagonalizable. And and there's no way to really fix this, but what we'll see is that we can choose our basis so that like this matrix isn't so bad, and we'll be able to find bases which give like matrices that look like this. Okay, so that's our plan. Anyways. Okay, so our plan is we want to find as many T invariant subspaces as we can. And then hopefully if we find enough, then T has like a special form. Okay. Just some basic properties of invariant subspaces. If U is T invariant and P is a polynomial, then I can plug T into the polynomial and apply that to U, and I get another T invariant subspace. I can also look at all the vectors V such that when I apply P of T, I land in U. That's also T invariant. And any subspace of an eigenspace is also T invariant. So let me give you a few typical examples. And then we'll prove one of these. Like, for example, it tells you that T of V is T invariant. It will also tell you that the kernel of T, which is all the vectors V such that T of V equals 0, is T invariant. It tells you that any eigenspace, like kernel of T minus C, which is all the vectors V such that T of V equals CV, this is T invariant. But it also tells you something like, tells you more that, like, for example, maybe kernel of T squared minus 1 is T invariant. And also like kernel of some other polynomial like T cubed plus T, or sorry, I should put like maybe T cubed plus T of V is T invariant. Okay. So so this kernel of T minus C, you can call that like the eigenspace corresponding to this scalar C. That's a T invariant subspace. That means if we have diagonalizable linear transformation, the fact that it's diagonalizable tells us that we have like kind of the best case scenario, which is we have a bunch of kind of invariant subspaces where T just acts like scalar multiplication. Okay. So let's see, how should we prove, like, let's prove that T of V is T invariant. So let's say that U is T of V. Well, then what's T of U? Well, it's just T of V. And T of V is contained in, so since T of V is contained in V, T of V is contained in T of V. Contained in T of V. In particular, T of U is a subset of U, so U is T invariant. Similar for kernel of T. If U equals the kernel of T, well then T of U is just the 0 subspace, and that is contained in U. Okay. So now let's P of Z be a polynomial, and let's just show like, let's let W equals P of T of U, and let's compute T of W. Let's just T P of T of U. And you can rewrite that as just P of T of U, and that is contained in P of T of U, since T of U is contained in U, and that equals W. P of T of U is W. Okay, and what this proof rests on is the fact that P of T times T equals T times P of T, which is just saying that, and that just follows from the fact that P of Z times Z is just the same as Z times P of Z as polynomials. Okay. So the reason why do we want to use these polynomials and check this kind of property? Well, we're going to find out why. Okay. Oh yeah, so you can kind of imagine that if a matrix or if a linear transformation is diagonalizable, then you have lots of invariant subspaces, okay? But also you have a lot of invariant subspaces if you have a triangular form for the matrix. Okay, so let's think about what a triangular matrix tells us. So I'll just, maybe we have like this triangular matrix. A upper is upper, or let's call it T for upper triangular. We have, you know, I don't want to say lambda 1, so I'll just say like T1, T11, T22, T33 to TNN. And then I have some stuff up here. And then I have zeros. So that T is upper triangular. Oh, I use T for linear transformation, so let me call this, instead of T, I will call it, let's just call it A. Okay. And then what is one way to think about this? Well, we just put W1 to be the span of E1. Notice that AE1 equals T11 times E1, which is in W1. Okay. So that tells you that W1 is a kind of an A invariant subspace. And then we can't just do, so now we just take W2 to be the span of E1, E2. And then notice that A times E2 is T22 times E2 plus some stuff times E1. And A times E1, already we know that it's in W1, which is contained in W2. This is in W2 as well. Okay, so A takes the linear combinations of E1 and E2 and gives you back linear combinations of E1 and E2. So that tells you that W2 is T invariant. And then you just put W3 to be the span of the first three basis vectors. And then you see that A times W3 is contained in W3. And you keep on going. and then you get bigger and bigger subspaces, and then Wn is just the span of E1 up to En, and this is also T invariant. This is all of V, so it's clearly T invariant. Okay. So finding this upper triangular form for A means finding kind of a sequence of T, or in this case, A invariant subspaces. Each one is kind of like one dimension bigger than the last one. Okay, and that gives you an upper triangular matrix. So all these scribbles up here means that when you take A times En, it might have some like terms involving all the other vectors. But it also tells you when you take A times En minus 1, it doesn't involve any Ens. Okay, so that's just an example. So, and yeah, now our plan is to not be satisfied with this scribble of things above the diagonal. What we want things to look like is, well, you can't really change the things on the diagonal, but we just want ones and zeros above the diagonal, basically. Okay, so that's our plan. Make turn these scribbles into something very simple in order to better understand what's going on. Okay. So we have this theorem called the primary decomposition theorem. And it says that if you have the characteristic polynomial of either a matrix or a linear transformation, and you do like the kernel of t minus lambda I to the power that occurs in the characteristic polynomial, or if it's a matrix, then you're looking at the null space of a minus lambda I to the mi, same thing. And you combine those, and then they give you a direct sum. The direct sum of those gives you V. And let me just tell you what this theorem tells us about like an example. Let's do an example before we talk about what's happening. So here's my example. Example, suppose a characteristic polynomial of my linear transformation T from V to V is some like polynomial like x minus 2 cubed times x plus 1 squared. Okay. Then I'll just put W. Well, I'll put W1. That's going to be the kernel of x minus 2 cubed. And W2, that's going to be the kernel. Oh, sorry, not x. T. T instead of x. And here, W2 is going to be the kernel of t plus 1 squared. And then now, when I find the matrix of T, what I get is a 3 by 3 matrix up here and a 2 by 2 matrix, right? This 2 by 2 matrix is corresponding to W2. The 3 by 3 is corresponding to W1 and zeros. And that's our plan. And then if even better, like as a corollary, if the characteristic polynomial of T has no repeated roots, then T is diagonalizable. like as an example, if the characteristic polynomial of t is x minus 1 times x plus 1, then this primary decomposition theorem tells us that we can take W1 equals the kernel of t minus 1, and W2 is the kernel of t plus 1. Now, if W is in W1, then T of W1, or sorry, T of W, or sorry, I should say T minus 1 times W is just 0, which tells you that TW equals W. Okay, so the matrix of T, if you restrict it to W1, is just like a diagonal matrix, all ones on the diagonal, and the matrix of T as it acts on W2 is all negative ones. Okay, just as an example. Okay, so how do we get this primary decomposition? We need this lemma, and then after we talk about the lemma, we'll probably take like a 5-minute break. Okay, so what's this lemma say? That if we have a matrix A, or a linear transformation is fine too, but if h of A equals 0, where h is some polynomial, and we can write h as f times g, where f and g have no common factors, and now W1 is going to be the null space of f of A, and W2 is going to be the null space of g of A, then V is the direct sum of W1 plus W2. Okay, that's our lemma. Okay, well, let's think about how to prove this for the simple case where h is t minus, or h is x minus 1 times x plus 1. And let's try to prove this. Okay. Let's try to prove for h equals x minus 1 times x plus 1. So we'll suppose that t minus 1 times t plus 1 equals 0. And we're going to put W1 to be the kernel of t minus 1, W2 to be the kernel of t plus 1. And we want to write every vector as something in kernel of t minus 1 times something in kernel of t plus 1. And the trick is that the GCD of x minus 1 times x plus 1, well, they have no, x minus 1 and x plus 1, they have no common factors, meaning when you factorize that, well, they're already factored into like linear products of linear things. Okay. So they're already factored into irreducibles, and they have like 2 different irreducible factors if you want. Okay. Another way to see this is that 1 is equal to a half times x minus 1. Oh, I want to a half times x plus 1 plus negative a half times x minus 1. Okay. So this equation, so you can just check that half times x plus 1 times plus negative a half times x minus 1 gives you 1. Okay. Then what happens when you plug in t? Well, you get that 1 is equal to a half times t plus 1 plus negative a half times t minus 1. And in particular, what happens? Well, you get v. If v is any vector, then v is just a half times t plus 1 of v plus negative a half times t minus 1 of v. And if you want, you can just take this equation and see that it, when you expand everything, you would just get v, you know? Okay, that's why we use, yeah. Okay. Now I will call this first vector, I'll call this first vector w1, and I'll call the second vector w2. What happens if I do t minus 1 of w1? Well, I get t minus 1 times a half of t plus 1 of v. That's just so t minus 1 is linear, so I can factor out the half. So I get t minus 1, t plus 1 of v. And t minus 1 times t plus 1 is just 0, so I get a half times 0 of v, which is just 0. Okay, so t minus 1 takes any vector that looks like t plus 1 of v and makes it 0. And t plus 1 does the same thing to w2. So if you work it out, you see that you get a half t plus 1, t minus 1 of v, which is the same as a half t minus 1 times t plus 1 of v, which is just 0, because t minus 1 times t plus 1 is 0. Okay, so our w1, that's in the kernel of t minus 1. So little w1 is in the subspace w1. Little w2 is in w2. That tells you that any vector is a sum of something in w1 plus something in w2. And how do we know it's unique? Well, if w is in both w1 and w2, then you just use this decomposition again and you write w equals a half t plus 1 of w plus negative a half t minus 1 of w, but little w is in w1, little w is in w2, which means that t plus 1 of w equals 0. It's in w1, which means t minus 1 of w equals 0. So you just get 0 plus 0 equals 0. So the only thing in both subspaces is 0, and the sum of the subspaces is the entire vector space V, so we have a direct sum. So V equals W1 plus W2. Okay, and in order to execute all these details, what we really needed is we needed an equation like this. And this equation follows from the fact that they're the two GCDs, the GCD of the two polynomials is 1. Oh yeah, and we also needed that when you multiply the two polynomials together, you get 0. Okay. So those three things is, well, really this fact, this one are the key points. Okay. So let's try and see how the lemma is proved. Right, so if GCD of f and g is equal to 1, that means we can find polynomials a and b such that af plus bg equals 1. And I'm not really going to ask you to find a and b, but if you did, it wouldn't be so bad. You have to do something called the Euclidean algorithm. You just do it for polynomials, and it turns out to be fine. Okay. Now, if you have that AF plus BG equals 1, you do the same thing. So you know, like, since f times g of a equals 0, when you apply g of a to v, you get something that's in the kernel of f of a. And when you apply f of a to v, you get something that's in the kernel of g of a. And now you write, well, if 1 equals af plus bg, then v is equal to a of a times f of a times v plus b of a times g of a times v. And then you just do the same thing. Like, if you apply g of a to this first term, you get 0. So this first term is in the kernel of g of a, or the null space of g of a. And the second term is in the null space of f of a. And you can do all the tricks that we did for the simple case on the whiteboard. Okay, and that tells you that you have a direct sum. Okay, and I see a question. So point 2. I do have g of a, 0.3. Okay, yeah, so if we have a and b are both polynomials. So like when we plug in a, we get a of a times f of a and b of a times g of a. But the point is, yeah, so the point is now when we multiply by g, the a doesn't matter anyways. In the simple case we did on the whiteboard, a, the polynomial, is really a half, and the other polynomial b was negative a half, but it could possibly be something more complicated, but it's fine. Okay. So let's take 5 minutes. Okay. Let's keep going. So what we're trying to do is apply this lemma, which says if you plug in either a matrix or a linear transformation into a polynomial and you get 0, and you can factor that polynomial somehow, then that gives you a decomposition of V into T invariant subspaces. Okay, and one way we know to get a polynomial which when you plug in A gives you 0 is a characteristic polynomial. Okay, so we know from the Cayley-Hamilton theorem that if you factorize a characteristic polynomial as, into a different, so you have all the different eigenvalues and they occur in like different powers in the characteristic polynomial. So what we're going to do is let F be all the occurrences of Z minus lambda 1 in a characteristic polynomial, and G is going to be whatever's left over. Okay, all the rest of the eigenvalues. Okay. Then F and G have no common factors. Okay, so their GCD equals 1. That means you can find like polynomials A and B such that A times F plus B times G equals 1. Okay, so basically you apply the lemma, and that tells you that the vector space V is the direct sum of the null space or kernel of F of A plus direct sum the null space of this more complicated thing, G of A. Okay, and then what you do is by induction, so the kernel of G of A has like less dimension than V does. So, you use induction. You say, well, like you assume that the theorem is true for all vector spaces with dimension less than V. So that tells you that W prime is the direct sum of, kernel of T minus lambda 2 to the M2 plus kernel of T minus lambda 3 to the M3 and so on. Okay. And then since W prime is the direct sum of those different kernels, and then V becomes the direct sum of Wn on all the rest. Okay. Okay. Okay, so right now our situation is that if we factorize the characteristic polynomial, each little factor of the characteristic polynomial gives us like some block. Okay. Some block of the matrix which doesn't interfere with any of the other blocks. Okay. And now we want to understand each individual block in this primary decomposition. Okay. And to do that, we need basically the Jordan normal form and Jordan blocks and things like that. So we just need a little definition. We're going to say that a matrix is nilpotent if n to the m is 0, is a 0 matrix. An example of a nilpotent matrix is our matrix A, which we wrote down at the beginning. Let me just remind you. Here's my matrix A. So A is 0, 1, 0, 0, 0, 1, 0, 0, 0, and a squared is 0, 0, 1, 0, 0, 0, 0, 0, 0, and a cubed is all zeros. Okay. So our matrix A, which we saw wasn't diagonalizable, well, although it's not diagonalizable, it is nilpotent. And nilpotent, well, nil I guess means zero, and potent means power, so it means like you take the power of it and you get zero. Okay. So what we want to do is we want to understand nilpotent linear transformations and nilpotent matrices. What is the reason for this? Well, we know that, so why do we want to understand these nilpotent matrices? Well, like for example, at this point, what we've done is we can write V. So if V is the kernel of T, let's say T minus 1 squared, direct sum kernel of T plus 1 cubed or something like that. And W1 is kernel of T minus 1 squared. Then if we let S be T minus 1, then we can think of S going from W1 to W1. And S squared is T minus 1 squared is 0 on W1. So that tells us that when we look at only vectors such that T minus 1 squared of V equals 0, that tells us that T minus 1 is a nilpotent matrix, or sorry, a nilpotent linear transformation on W1. Okay. And on this second term, kernel of T plus 1 cubed, T plus 1 will be, T plus 1 cubed will be 0. So again, T plus 1 is going to be a nilpotent linear transformation, or it's going to correspond to a nilpotent matrix. Okay. So because we have the primary decomposition, our next step is to understand nilpotent matrices or nilpotent linear transformations. Okay. Okay. We head back to the Jordan, right? So we have these three equivalent things. If A is an n by n matrix, the following are equivalent. So A minus lambda is nilpotent, meaning like A minus lambda to some power equals 0. Okay. Another condition is that the characteristic polynomial of A just looks like z minus lambda to the power n. So and another way of saying that is the only eigenvalue of A is lambda. Okay. And okay. So we want to, so if we have some eigenvalue of lambda, the reason we want to study nilpotent matrices is because we want to look at A minus lambda. Once we figure out the structure of A minus lambda as a nilpotent matrix, well, whatever that structure is, we just add lambda times the identity to both sides, and we learn about A. So that's our plan. Okay, then we have this definition seems to come out of nowhere, but here it is. So let's start with a nilpotent linear transformation, or a nilpotent matrix if you want. And so that means that t to the n, or sorry, we're going to say like t to the k is going to be 0. And let's suppose that we have a vector v such that t to the k of v is 0, but t to the k minus 1 of v is not 0. Then we're going to call c of v to be the span of all these vectors. So it's the span of v, t of v, t to the k minus 1 of v. And this thing c of v is going to be called a cyclic subspace of v. Okay. And I just want to tell you a little reason why we should call it a cyclic subspace. Okay, so suppose t to the k of v equals 0 and t to the k minus 1 of v is not equal to 0. Let w be in c of v, which is in the span of v, tv, t squared v, up to t to the k minus 1 v. Okay, that means that w equals c0v plus c1 times t of v all the way up to ck minus 1. I'll try my best to write that. ck minus 1 times t to the k minus 1 of v. If I rewrite that, well, that's just equal to c0 plus c1t plus c2 t squared plus t to the k minus plus ck minus 1 t to the k minus 1 evaluated at v. So it's just some polynomial of t evaluated at v. So we can just rewrite that as p of t times v. Okay. So any vector in the cyclic subspace is a polynomial of t applied at our vector v that we started with. Okay. Furthermore, since t to the k of v equals 0, if q of z is any polynomial, you can show that q of t of v is also in c of v. So the cyclic subspace is what you get if you start with the vector v and allow yourself to apply polynomials, any like polynomial in t to v. Okay. Okay, and then what we want to see next is how a cyclic subspace ties back to like this special kind of matrix which we've seen. So let's go back to it. Okay, so we have this proposition. If we have a cyclic subspace, remember that just means that t to the k of v equals 0, but t to the k minus 1 of v is not equal to 0. Okay, so we have a cyclic subspace. Then, so the cyclic subspace is the span of the v, t of v, t squared of v, all the way up to t to the k minus 1 of v. But this proposition says that under these conditions, that t to the k of v equals 0 and t to the k minus 1 of v is non-zero, then this b is a basis for you, for the cyclic subspace. And the matrix of t on the cyclic subspace is this matrix with ones above the diagonal and zeros on the diagonal, zeros everywhere else. Okay, so nilpotent linear transformations that act on cyclic subspaces have this special matrix. They have a special matrix. Okay. So, you know, it doesn't take too long to prove this, so let's try it. So we know, so consider C0 times V plus C1 times T of V plus C K minus 1 T to the K minus 1 of V equals 0. We want to show that V, T of V, T squared of V, and so on are linearly independent. That means we need to look at this equation and show that all the C's are 0. Okay, but if I apply T to the K minus 1 to both sides, on the left-hand side, I have C0 T to the K minus 1 V plus C1 T to the K of V plus C2 T to the K plus 1 V, and so on. On the right-hand side, I have T to the K minus 1 of 0, which is just 0. But T to the K is 0, T to the K plus 1, that's 0. Like T to the K of V is 0, T to the K plus 1 of V is 0, and so on. So this simplifies to just C0 times T to the K minus 1 of V equals 0. But T to the K minus 1 of V is non-zero. That's our assumption about V was that T to the K of V is 0, T to the K minus 1 of V is non-zero. Okay, so some scalar times a non-zero vector equals 0. That means the scalar equals 0. Okay, so we go back to our original equation. Our original equation really says just that C1 times T of V all the way up to CK minus 1 of T to the K minus 1 of V equals 0. Okay, now we apply T to the K minus 1, or sorry, T to the K minus 2 to both sides. Once we apply T to the K minus 2 to both sides, well, everything disappears except C1. So we just apply T to the K minus 2 to both sides. And the same thing happens. You just get C1 times T to the K minus 1 of V equals 0. So that tells you that C1 equals 0. Well, now if you go back to the original equation, now you're left with C2 times T squared of V. And you just keep on doing the same thing. So that equation you multiply by T to the K minus 3. That tells you that C2 equals 0. You just keep on going. Eventually, you show that C0 is C1 is C2 is CK minus 1 equals 0. So all the coefficients are 0, so these vectors are linearly independent. Now let's think about what is the matrix of T relative to this basis. And actually, I wrote my basis backwards. I want this basis to be T to the K minus 1 V, T to the K minus 2 V, T of V, V. Now, T of T to the K minus 1 of V is just T to the K of V is just 0. So T of my first basis vector is 0. So that tells me that the first column, so this equation tells me that the first column of the matrix of my linear transformation is all zeros. So this tells me first column of matrix is all zeros. Okay. T of the second basis vector, that gives me the second column of the matrix. So what is T of T to the K minus 2 of V? Well, that's just T to the K minus 1 of V. And that is just the first vector that I wrote down. So that means that t of the second basis vector is 1 times the first basis vector plus 0 times the rest, plus zeros. So that tells me that the second column of my matrix of t is 1 and then all zeros. Another name for that is the standard basis vector E1, 1 followed by zeros. Well, t of the third basis vector, what is that? That's just t to the k minus 2 of v. That's the second basis vector. So that tells me that t of the third basis vector is the second basis vector. So the coordinates of that is a 0. So the coordinates, the third column goes like 0, then 1, then all zeros after. Okay. And if you are keeping track of the pattern is the one that we wrote down as J sub k. First column is all zeros. The second column is E1. Third column is E2. If you want, it's like I took the identity matrix and shifted it over, like I shifted everything over either one to the right or one row up, and then added a row of zeros or a column of zeros. Okay. So this basis should be in the reverse order in order to get this matrix JK. If you write the basis like this, the ones are really up below the diagonal, so that's a typo. Sorry about that. Okay. So if we can prove that if we can find lots of cyclic subspaces, then the matrix of T will be very simple. It'll just be like involve a lot of ones just above the diagonal and zeros everywhere else. Okay, so let's try and do that. Okay, so first we have a definition. A Jordan block of size K is just the matrix. This should be JK occurring here. So this J sub K is going to be called a Jordan block of size K. Okay, and if lambda is any scalar, we put J sub K of lambda, just like we just adjust our Jordan block by putting lambdas along the diagonal. Okay. And our goal is to find that if T is a linear transformation, we want to find a block diagonal matrix where all the blocks are Jordan blocks. Okay. Okay, so that's our plan. We want as many Jordan blocks as we can get. And to do that, we have this theorem. It says if we have a nilpotent linear transformation on a finite dimensional vector space, then V is the direct sum of cyclic subspaces. And that tells us that the matrix of T is going to be like a bunch of Jordan blocks going down the diagonal and zeros everywhere else. Okay. Okay, so we need to show that V is going to be the direct sum of cyclic subspaces. And we do that by induction. Okay. So, first of all, if V has dimension 1 and T is nilpotent, then T is actually equal to 0. So any basis of V will give us like any vector will give any non-zero vector will give us a cyclic like a direct sum of cyclic subspaces. Okay, so all that is to say that if the dimension of V is 1, then this theorem is kind of trivial. Okay, so now we use induction. We're going to assume that the theorem holds for all V primes having dimension less than the dimension of V. And then we'll use a particular one. So now we're going to suppose that V is a given vector space that such that T is nilpotent. And we're going to let V prime be T of V. And then since T is nilpotent, the kernel of T has to be non-trivial. Okay, because what does nilpotent mean? It means that T to the M equals 0. Okay, that means that the only eigenvalue of T is 0. And if the only eigenvalue of T is 0, it means that there's an eigenvector for that eigenvalue, and like the eigenvector will just be in the null space or the kernel. Okay, so if T is nilpotent, T has non-trivial kernel, which means that it cannot be onto. Okay, and so this V prime has dimension strictly less than the dimension of V. So therefore, V prime is the direct sum of cyclic subspaces. And for each one, so again, V prime is all the things that look like T of V. So each V1, so V1 we can write it as T of W1, V2 we can write it as T of W2, and so on. And then we just construct this subspace W prime, which is the cyclic subspace generated by all the W's. And notice that T of W prime is T of V, which is V prime. Okay, and you have to prove that this W prime is a direct sum. And it is just like a trick to it that I'm just going to skip, I guess. So when I say a trick, I mean like to prove that this W prime is a direct sum. For me, I'm always forgetting what the trick is. I remember now, but I'm just saying like doesn't really illuminate things for me, but anyways. So there's some trick which allows you to prove that W prime is the direct sum of these cyclic subspaces. And now, since T of W prime equals T of V, you can find a subspace of the kernel of T to give you all of V, right? And I want to explain that briefly, at least that part, even though I didn't explain the rest. Okay, so right, so let's just explain. Let's just suppose T of W prime equals T of V. And we want to show that V equals W prime plus U, where basically T of U equals 0. Okay. So let V be in V. Now T of V is in T of capital V, which is T of W prime. So you can write T of V equals T of W equals T of W for some W in W prime. Now I'll let U equals V minus W. Then T of U is T of V minus T of W equals well, T of V equals T of W, so this is 0. So U is in kernel of T. Now V equals W plus V minus W, where W is in W prime and V minus W is in kernel of T. Okay. Now it doesn't mean that, so so what we can do is we can find a subspace of kernel of T such that V equals W prime direct sum U. Okay. Okay. Okay, and so we have, so now we've shown that a nilpotent matrix, or sorry, a nilpotent linear transformation, you can decompose V as a bunch of cyclic subspaces. Okay, so now we can make our definition. Okay, so our situation is we have a linear transformation from V to V. The characteristic polynomial of T is going to be like Z minus lambda 1 to the M1, Z minus lambda 2 to the M2, and on like that. We put Wi to be the kernel of T minus lambda I to the Mi. And then for each Wi, we see that T minus lambda I is nilpotent on Wi. So we write Wi as the direct sum of cyclic subspaces for each Wi. And then we do that for all the different Wi's. And then, so we get a Jordan basis for each Wi. Basically, yeah, and then we combine them all to get a big, huge Jordan basis for T. Okay. Oh yeah, so let us just kind of try and describe what might happen. Okay. Just for example, let's say that A is a 6x6 matrix, and suppose the characteristic polynomial of A is, so a 6x6 matrix has a 6th degree polynomial, characteristic polynomial. So its characteristic polynomial might be like Z minus 3 cubed, Z minus, or let's say like Z squared. And then the last term, I have one left over, so maybe like Z plus 4. Okay. Okay. So we're going to put W1 to be, that's going to be the null space of A minus 3 times I cubed. W2 is going to be the null space of A squared. And W3 is going to be the null space of a plus 4 times the identity. Okay. And what we know is that this first W1 has dimension 3, W2 has dimension 2, W3 has dimension 1. Okay. Okay. So now we suppose like now kind of like if we look at a minus 3i restricted to W1, it's going to be a nilpotent linear transformation. So it's going to be the direct sum of cyclic subspaces. So let's suppose that W1 equals, you know, it might be W1 might have a Jordan basis of the form, let's say V, and then T minus, or sorry, A minus 3i times V, and then a different vector, let's call it W. Okay, and W2 has a Jordan basis of the form, I guess I'll use U, so it'll be U, AU. And W3 has a Jordan basis, well, any basis of W3 will work, so that'll be of the form. So I have UVW, I guess X. Okay. So then what do I do? Well, I construct my basis B to be, I put W, then I put A minus 3i, V, then I put V, then I have AU, and then I have U, and then I have X. Okay. And then, well, if I have a basis for, so this is going to be a basis of, R6. Okay, I have 6 vectors, so this should be a 6-dimensional vector space. Okay. And then I just do the same thing that we would do if we were trying to diagonalize. So I put P to be the matrix whose columns are these vectors that I wrote of B. So we have W, A minus 3i, V, and then V, and then AU, and then U, and then X. So in columns. And then you see that A times P is equal to AW, A minus A times A minus 3i times W, or sorry, times V, then AV, and then A square, A times AU, then AU, then AX. Okay. But so my Jordan basis for W1, the fact that it's of the form V, A minus 3IV, and W means that A minus 3I W equals 0. So AW is just 3W. So you get 3W, and then A times A minus 3I times V is just 3 times A minus 3I times V. And then AV oh wait, this should be yeah, and then AV gives me 3 times V plus A minus 3I times V And then A times AU is 0. AU is just AU, and then AX is 0. And then what it turns out is that this is kind of like the matrix. So if you can write it as, so AP is going to be P times the matrix, which I'll try and write down now. So you have 3, and then you have 3, 3, 1, and then you have 0, 1, 0, and then you have, oh, sorry, A times X is just 4X, not 0, so that should be 4X. And you have 4. Okay, so you have P times this matrix. And this matrix, you can it's like, looks like it is a block diagonal form. So like it's not really a diagonal matrix because there's things like slightly off the diagonal. But you can think of it as a block diagonal matrix. And the blocks are these Jordan blocks. Okay. Okay. So, you know, basically A times P is P times this Jordan, like this block diagonal matrix. So you would write like, so basically we have a factorization A equals P D P inverse, but the D is not diagonal, but it's like almost diagonal. Okay, we just have these little ones. And we see like sometimes you can't get rid of those ones because those ones kind of are telling you that your matrix is not diagonalizable. Okay. And we're pretty much out of time, but I also wanted to tell you the last thing is that, okay, so this theorem is what I was just explaining, but what you can show is that the Jordan blocks are unique. Well, except for that you can kind of rearrange their order, but you can't change how many they are and how big they are. And so to prove that is not so hard, but I'm going to probably put that in its own separate thing. Okay, so so that's pretty much it for today. Yeah, I'll try and put like some kind of more examples. I'll try and upload some videos on the weekend about this topic. So that it's not so abstract. Well, it's still pretty abstract anyways. Oh well. Okay, so I guess that's it for today. You know, thank you everyone for staying with me. Okay. Yeah, so look out for assignment 5 tomorrow. Yep, that's it. Okay. Bye.